starting out with chapter 7 here. I'm actually not going to show you the video, but if you click on this little image here, you can actually see a YouTube video which just shows you in animation how these conic sections are formed. But basically the idea is that if you take, this is what we call as a right circular cone. So if you take two of them and you just take a cross section with the plane, depending on how the angle of the plane interacts with the right circular cone, you end up getting these conic sections. So it's coming from the idea of taking a section out of a cone to get a conic section. So the idea is if you just look at one right circular cone and that plane is going to cross the cone at an angle, that's basically how we are getting a parabola out of that. If I, at a 90-degree angle, if that plane crosses the cone, then that's how, because you can see this is at an angle, but this one is basically horizontally cutting it. That's how you get a circle. An ellipse is basically, instead of horizontal, if you tilt that plane a little bit, but you're not going all the way to the end of the cone, then you're going to get an ellipse. And then, of course, a hyperbola will always have two parts to it. So it's basically vertically cutting through the double circular cone. And that's where you get the two branches of your hyperbola. The properties between a hyperbola and a parabola are very, very different. So even though in general shape, they might look like they're very similar, in properties, they are not. So they end up being a little bit different. So the first section, we're actually starting out with a parabola. Now, of course, we're familiar with the equations of a parabola, y equals ax squared plus bx plus c, or in the transformation form, we have y equals a parentheses x minus h squared plus k. Now, we don't really have any new equations for a parabola here, so obviously we just use those two. But in terms of a conic section, we define a parabola as a set of points in the plane that are equidistant from a fixed line. When we're talking about the fixed line, we're talking about this line, and a fixed point which is not on that line, and we call that a focus. So we're basically saying all the set of points that your parabola has is going to be the same distance. So if I pick a random point here on the parabola, the distance from this point to the focus and this point to the directrix should be the same. That's what they're saying when they're saying equidistant. So here, we're actually bringing in some new terminology and some new parts of a parabola, which is the directrix. That's this line over here. In this case, you can think of it obviously as being perpendicular to your axis of symmetry in a way, and then a focus also to our parabola. Now, the important thing to remember here is from the vertex of our parabola to the focus, and from the vertex of our parabola to the directrix, that distance is always going to be the same, and that's a big part of what we'll be doing in this section here. So why do we need to worry about the directrix and the focus for a parabola? Basically, the idea is when we start looking into the reflective properties of a parabola, it really makes a big difference of where the directrix and where the focus of your parabola is, especially the focus. So you can think of applications that are happening with a parabola, and I don't know if I have those mentioned over here. Yeah, so you can think about spotlights. The reflective surface is going to be your parabola shape. You can think about, I believe we've got flashlights in there, telephoto camera lenses, radio antennas, satellite dishes, for that matter, eavesdropping devices. All of these are using this reflective property of a parabola, because think about a satellite dish. If you take a cross section of that satellite dish, you're basically getting a parabola, and where we have those receivers on our satellite dishes or even eavesdropping devices, because they use the same idea, that receiver is going to be right at the focus. of this parabola. When we're talking about spotlights, it actually works in a reverse way, because the spotlight is placed where the focus of our parabola should be. So what happens is that spotlight reflects on the mirror surface, and that's why, you know, that light magnifies so much, like when we use them at games and, you know, at events and stuff like that. Same idea with the flashlight. Where is that little bulb on a flashlight? It's right at where the focus should be, because the idea is if this is a spotlight or a flashlight, this is my light source right here at the focus. So in this case, the arrows would be going in the opposite direction. So from here, our light would be hitting this parabolic surface, and it's going to get reflected out. In telescopes, what's happening is, if we talk about, you know, getting a light from some distant planet, then basically the idea is that light is coming from the distant planet, it's hitting this reflective surface, and it's being reflected into the focus, and that's usually where we'll put either another mirror or an eyepiece or something, so that we can now see this distant object. So that's kind of why we're actually talking about conic sections and what a parabola with its focus ends up looking like. So let's actually look at this example here. They're asking us to find the equation of a parabola if we are given the focus and the directrix. Now again, remember the directrix is just this line, which is the same distance on the opposite side from your focus. So just some basic definitions that we should be familiar with. Now, when our equation is given to us in this transformation form, remember our vertex is always at the values of h and k from there, right? Now, you should be able to see whether a parabola opens up or down. Our vertex and focus are always going to be vertically in line with each other, right? Which means our focus and our vertex have the same x-coordinate. Both of those are h. Vertex is k, but the focus will be k plus p. Now this distance p is basically talking about this distance here between your focus and the vertex. So right here, this distance between the focus and the vertex is what we call as distance p. Directrix is this line, which will be the same distance p away from your vertex. So whether it's down below the parabola or above the parabola, again, this line is going to have this equation, y equals k minus p, okay? So k plus p is going to be part of the focus, k minus p is going to be part of the directrix, okay? The relationship between our a value for the parabola, which is this a right here, ax squared plus bx plus c, or you can think about the a in terms of our transformation, is going to be a equals 1 over 4p. Okay, so those are some things we're definitely going to need to keep track of when we are looking at this. So for the focus of our parabola, it's h comma k plus p, right? Because it's an ordered pair. So that's how you write it down. The directrix of our parabola is going to be a horizontal line, which will be k minus p. The relationship between a and p is a equals 1 over, 1 divided by 4p. And let's not forget that the vertex of our parabola is always at hk, okay? So looking at that first problem, they're asking us to find the equation of the parabola, right? Based on the focus and the directrix. So let's see how we can solve our first example. Okay. So focus is given to us as 3, 5. Directrix is given to us, what was was that y equals 2? Okay, so remember how focus is defined as h and k plus p, and directrix is defined as y equals k minus p. So if we needed to find the equation of the parabola, we will actually do that in this form. Okay. And we need to use all of these different relationships that we were looking at. So luckily, we already know what the value of h is, because h is going to be this first coordinate from our focus. So we already know h is 3, which means to be able to find the equation of our parabola here, we need to find the value of k, and we need to find the value of a. Once we have all 3 of those, we can come up with the equation of our parabola here. So the value of k is what we're going to go for next, and that's actually going to come from this k plus p and k minus p values, okay? So looking here, I've got k plus p, which will be 5, and I've got k minus p, which represents 2. And you know how in the last chapter we talked about solving systems of equations? That's exactly what we're going to do here. So we've got 2 equations here. If we actually just go ahead and add them as is, what we have written down, what do you see happening here when I add the 2 equations? Yeah, 2k, right? Because it's k plus k. So we've got a positive p and a negative p. They should automatically cancel each other out. K plus k will become 2k. 5 plus 2 will become 7. Divide by 2 so we can get k by itself. And leave that as a fraction. So now we have our k value. The only thing remaining is finding a, right? And a is so what's the step involved if we needed to convert this from transformation into standard, which is y equals ax squared plus bx plus c? Okay, if they ask you to convert it, the first thing we do inside the parentheses is FOIL. So that will end up giving us, what will that be? X squared minus 6x plus 9. And then the plus 7 halves at the end. Go ahead and distribute this 1/6 inside the parentheses, which will give us 1/6 x squared. 6 and 6 will actually cancel out, giving you negative x in the middle. 9 divided by 6 will reduce down to 3 halves, and then that plus 7 halves at the end. What will that be? 10 divided by 2. 1/6 x squared minus x plus 5. So depending on what your instructions are, you can have your equation in this form, but if they say specifically standard form, that's your standard form. Okay, so you just kind of follow the instructions. Obviously, if they want it in this one, then you're done. You don't have to worry about cleaning it up, right? Okay. Questions on number 1? Okay, you're not going to have to worry about this guy here. Okay, so we're going to skip 2 and actually get into this graphing right here. Okay, so this one is saying, find the vertex, find the axis of symmetry, find the X and Y intercepts, and sketch the graph showing the focus and the directrix. Okay, so how do we come up with a graph when you are given the focus and the directrix? A lot of it is actually going to be somewhat similar to what we did here. So let's go ahead and write down what information we have. So they're telling us the focus is -1, 35/4. The directrix is y equals 37/4. Just so we kind of know where these values are, can you tell me the decimal approximations for 35/4 and 37/4?
8.75.
For 35/4? Okay.
9.25.
Okay. So okay, that was not a very nice graph. Let's try that one more time. Okay, so if they are telling us that the focus is going to be at 8.75, and of course that's with the ordered pair, -1, so that's going to be, if this was -1, 8.75 will be somewhere over here, okay, just approximately. We know directrix is going to be a horizontal line, which is at 9.25, so that's going to be 9.25, somewhere over there. We know halfway between the focus and the directrix is our vertex, because remember I was telling you guys that here, if you think in terms of the distance, that's the same distance between the focus and the vertex, and the same distance between the vertex and the directrix. So basically the idea is, what is halfway between 8.75 and 9.25? 9. Okay, and how did we come up with that? Because I want to make sure all of you are able to do that. So how do you find halfway between 8.75 and 9.25? Either, think about it, the difference is I'm going a quarter above 9 and a quarter below 9, right? So just going quarter on each side, which means right at 9, I should have my vertex. The other thing you can do is add the two numbers and divide by 2, right? Because you basically end up adding 9 plus 9, which gives you 18. 18 divided by 2 is 9. So to find the focus, remember the focus and, sorry, not the focus, the vertex. The vertex is always going to be in line with your focus, which means this x value is the same for your vertex, okay? And then, as I said, halfway between focus and directrix is your vertex. So to get this number 9, you can basically take 9.25, add 8.75, and then divide that by 2. Okay? Because then you don't have to actually go through. Whoa, no. Because if you use the idea of halfway between them, you don't have to do this. Okay, so this was a formal way of showing you, but this, what I'm showing you in the next example, is the shortcut way, okay? Okay, so we have our vertex. What else did they ask us to find? Axis of symmetry. Axis of symmetry, hopefully, is something you remember from chapter, what was it, 3? Axis of symmetry is the vertical line that passes through the vertex of our parabola. So it's going to be x equals what number? -1, yeah, because it passes right through the x-coordinate of your vertex, and now in this case the focus also. So axis of symmetry is -1, which actually will be this vertical line. Oh, and I'm a little off, aren't I? So that's my focus, my directrix. Let's put our vertex right at -1 and 9. Okay, I believe they also asked us to find the x and y intercepts. So if you're going to find the x and y intercepts, what do we need? Let's say if we did a table, we would still need something to help us with the table.
The equation.
You would need the equation. Yeah, so what we actually need here, we have our h and k values, right? The only thing we're missing is the a value to complete our equation. So let's find a next. And again, remember the relationship for a and p values is a equals 1/4p. Do you know for our specific example, what's the value of p?
1/4.
Yeah, it's 1/4, right? Because that's how far away our vertex is from the focus, or our vertex is from the directrix. So remember, p is the difference from vertex to focus, which would be in terms of the y value or the distance between the vertex and the directrix. So here, our p value, you can basically see is coming from here, is 1/4 or 0.25. Anybody who does not see where we got the p value from? Basically, just how far away are these two numbers? Or you can also do how far away is 9 from 875, or how far away is 9 from 925. It should be the same thing. And you don't have to worry about positive or negative in this case, because we're just talking in terms of distance, so we don't have to worry. We just need to know if it's going to be above or below. So since our p is 1/4, what does the a value come out to be? 1, yeah, because these guys cancel each other out. So a is 1. H was -1. And k is 9. So our equation ends up being, since this is a 1, I don't have to write it out, so I can just say x, negative and negative becomes positive, so that's x plus 1 squared plus 9. So using this equation, can you tell me what our x and y intercepts are going to be? So for x-intercept, make your y value 0. For y-intercept, make your x value 0. So take a couple seconds and let me see what you guys come up with. So if you make your y value 0, you basically end up with 0 equals and what are we seeing for the x-intercept? Does anybody have an answer?
or it's
It does.
undefined?
Actually, it is defined. There will be two
Rational?
happy points. Okay, first thing, start by moving that 9 to the other side, right? Oh, what happened?
Are you supposed to foil or?
I didn't really write down how I came up with that. Oh, no, I missed a step here. Okay, so this is what I missed, and this is why you were thinking irrational. When our parabola opens up, the focus is going to be above the directrix, right? When the parabola opens down, the focus is going to be below the directrix. So what's happening in our example is the focus, which is this red dot here, is below our directrix, right? Which means our A value actually ends up being a negative 1, because it's a parabola that's opening down. So since it's a parabola that opens down, we should have a negative sign in front of our parentheses in the equation. So that negative sign is basically what's going to help us not get into bad numbers, right?
Okay, now it can become a happy.
Yes, it can become a happy number. So basically just divide both sides by -1. The two negatives will basically cancel out, giving us +9 and positive x plus 1 squared. So now that when we take square root on both sides, we get a positive and negative square root of 9, which is positive or -3. So what are those two x values going to be?
Zero, 2, and 0.
Yeah, because +3 minus 1 will give us +2. -3 and -1 will give us -4, right? So two ordered pairs will be 2, 0 and -4, 0. So 2, 0 and -4, 0. So that's where our two x intercepts should be. Now we actually honestly just really need to know where should our graph be crossing the y-axis at, right? Yeah.
I just have a question, because
Yeah.
you use like a similar reasoning to the distance from the, could you use, you know that the x-intercepts are the same distance from the
Axis of symmetry.
and then use that to find, I don't know.
Well,
Where
you would know that they are the same distance, but do you only go 1 unit away from the axis of symmetry, 2 units away, or 3 units away, right? So I guess the idea is if you can find even one x-intercept, then you can use the same idea of symmetry to find the other one. But you still at least need to know how far you need to be away from the axis of symmetry. Does that make sense?
Yeah.
Yeah? Okay. Anybody else?
For where you said it becomes -1.
Yeah.
Is there any other way to find that out besides looking at your directrix and your
In
focus?
this example, because they're not giving us the equations, right? So it's only looking at, is the focus above the directrix? If the focus is above, parabola opens up. If the focus is below, parabola opens down. And so it's just looking at how the focus and directrix comes out to be. Okay, same calculation for y-intercept. Just make your x value 0. Come on. So in this case, that would become y equals negative. X is going to now become a 0 plus 1 squared plus 9. So 0 plus 1 will be 1. 1 squared is 1. This negative sign is outside of the square, which means the negative sign will stay. So it just basically ends up becoming negative 1 plus 9, which will be 8. So our y-intercept is at 0, 8. So right there. Okay, so we've got in the green is actually my vertex. So from that vertex, going down to 0, 8, and then of course crossing, our y-intercept. Let's see if I can do that a little bit better. Okay, and then from here, going down that negative 4. On this side. So the two x-intercepts, the y-intercept, and the vertex is honestly what we need to be able to come up with our graph in this case, and then of course finding all the other values that they were asking us to find. Okay. Questions on these two examples? So, of course, all the other properties for parabola will stay talking about symmetry, the portions where they increase, decrease. I mean, all of those properties are the same, but in this section, we're basically just interested in basically where the focus of your parabola falls, because in terms of that reflective properties, we need to know where the focus is going to be, because then we know how your graph is going to reflect in, like we were saying, in terms of if it's a satellite dish, if it's a flashlight, a spotlight, telescope, whatever other application you might have. So these ones we're talking about parabolas opening to the left and right. We're not going to worry about it. And these were just some examples showing you how the reflective property of a parabola comes into play. Obviously, we're not calculating this right now, but I just kind of wanted you to know that this is basically where the big part of its application is based, is in that reflections. Okay? But these are the only two types of examples you should expect to see in section 1 for 7.2. All right, let's get into our next shape. So ellipse and a circle. This little illustration is actually just showing you how you can draw an ellipse. So the idea is you can just basically tie a string to 2 nails, or in this case it looks like they're using tack pins. In the same line horizontally, just tuck them in, on a piece of paper, piece of wood, whatever, and then take your pencil through that string and just go ahead and draw your elliptical shape. Now the idea is the 2 places where we tacked these nails or tack pins at ends up becoming the foci, or the focus for the ellipse. Now an ellipse will have its own reflective property. It's going to be a little bit different than the parabola, because obviously a parabola is open-ended. One side of the parabola is open, so the reflective property is a little bit different. But ellipse being a closed shape, the idea here is if light or sound originates at one focus, it's going to bounce off this elliptical walls, and it actually ends up focusing or is directed towards the other focus. So it originates at one focus, and it reflects off the elliptical sides and goes and meets at the other focus. So I've never had a chance to actually try this, but the Capitol building in Washington, D.C. has a whispering gallery. Yeah, whispering gallery. So the idea is we think of the dome as actually a circle, but it's an elliptical ceiling, that Capitol dome that you have. So if you ever have had a chance, or if you in the future end up going, look for that whispering gallery, because the idea is if you're standing here at this focus and talking, nobody else in the room can actually hear you. So if I'm standing somewhere here, I can't hear a word. But if I happen to be standing right here where the other focus is, people who are talking right here, you can actually hear them only at that other focus because of that reflective property. So it can happen with sound, but it can also happen with light. And I think we're talking about the light here in terms of, oh, is it in a dentist slide? Somewhere I have it. I can't find it. Oh, yeah, dentist light. So that's basically, but you know what? I don't know if that's true anymore, because every time my mom goes to a doctor's office, to her dentist, that's all I do is look at the light to see how the reflection is working. To me, it looks like the light is right in the center of that little shape they have. So I'm not sure if that's true anymore, but I keep looking every time I go to a new dentist office to see if anybody's using that. So look for it. So the idea is same thing, right? The light should be starting at one location, bouncing off that little mirror reflection of the dentist light and concentrating at the other end. Obviously, the Earth orbits around the sun in an ellipse, and of course all other planets also rotate or orbit around the sun as an ellipse. Our satellite, so our moon, uses our center of the Earth as one of the focus points, and so the moon also orbits around the Earth in an elliptical shape, and so do any satellites that we send out into space. International Space Station, same thing, it's using the center of the Earth as one of the elliptical focus and orbiting with respect to that. So just as a definition, we are saying an ellipse is a set of points in the plane such that the sum of their distances from two fixed points is a constant. Each fixed point is called a focus, or of course plural would be foci. Now, just like we have parabolas that can open up and down, or that can open left and right, with ellipses, you can have sort of this shape, which is what we call as having a horizontal major axis. So that means it's kind of horizontally oriented. But then you can also have okay. What happened to my other pages? There we go. You can also have ellipses that open with a vertical major axis. So a little bit of your equation will actually change depending on is the ellipse horizontal or is the ellipse a vertical. So looking at some terminology here, we use the letter C to identify where the focus is going to be. So when it's positive C, of course, you're looking at the positive side of your graph. Negative C, so we usually label our foci as C, 0 or negative C, 0. We use B in this case to talk about the y-intercepts, and the V1, V2 that they're calling it here is going to be your x intercepts. So you can have negative C, positive C for the foci, positive B, negative B for the y-intercepts, they're not really defining it, but the positive A, positive B will be your x-intercepts. They actually talk about it more as x-intercepts when you're okay, what do I want to say? We're using the B for y-intercepts when your graph is opening horizontally. We're using B as your x-intercepts when the graph opens vertically. So what happens is the value of A will be an x-intercept when it's horizontal. The value of A will become the y-intercept when it's vertical. So they actually change places. And you should notice that in how we are writing our equation. So when it's a horizontal major axis, our equation for an ellipse is defined as x squared over a squared plus b squared over y squared over b squared equals 1 when it's a vertical. Notice how my denominators have changed places now. So the value that's under x, basically the easiest way to remember is the value under x will represent x-intercepts. The value that's under b represents y-intercepts. So that means now that my b is underneath x for the vertical one, the values of b, positive and negative, will become your x-intercept. The values of a will end up becoming your y-intercept. So they actually end up switching places. Another thing to remember, because you know when you're looking at the equation for an ellipse, it's not going to be in terms of a and b. It's going to be x squared over 9 plus y squared over 16 equals 1. So you actually have to see which variable x or y has the larger denominator. The one that has the larger denominator, that's the horizontal axis or the vertical axis. So if my larger denominator is under x, I'm going to have a horizontal major axis. If my larger denominator is under y, I'm going to have a vertical major axis, because that's the only way you can tell what kind of an ellipse you're going to have. Another thing that you need to remember when you're working with ellipses is this relationship between your a, b, and c variables. So a squared equals b squared plus c squared. When we get into hyperbolas, that relationship will change. So we need to be able to keep straight. What's the relationship for ellipses? What's the relationship for hyperbolas? So for an ellipse, you're always going to have that plus sign in the middle, okay? The larger denominator is under whichever variable. That's what your horizontal axis will be or vertical axis will be. And then the relationship between the a, b, and c variables. A squared equals b squared plus c squared. So when they give us something like this, they're asking us to graph our ellipse here, which actually will not be too bad. Okay, so let's see how to graph this guy. They are telling us, go graph and find the equation, wasn't it? Yeah. So they're giving us the foci, so that's the plural, is at -2, 0, and 2, 0. And we've got y-intercepts at 0, -3, and 0, 3. Okay? So on our graph, so y-intercepts are at 0, 3, 0, -3. So that's basically where our ellipse will be crossing, right? The y-axis at. Foci are actually at -2, 0, and 2, 0, which means your foci are falling on the x-axis, which means we do actually have a horizontal major axis because your foci are always going to be on the major axis. So at 2, 0, and negative 2, 0 is where the foci are. So somewhere on the x-axis, we gotta basically figure out where are they crossing the x-axis at. So this is where that relationship between our A, B, and C will come into play. So remember, for foci, these numbers represent our C values. And then were the y-intercepts the B or the A? You can go back and look at page 2 of your handout with that first box. You will see we're defining y-intercepts as 0, negative B, and 0B, right? So these guys are your B variables. So basically they're telling us C is 2 and B is 3. You don't have to worry about the negative parts because we square everything. The relationship between A, B, and C is what's the important one here. So that was defined as A squared equals B squared plus C squared. Kind of like the Pythagorean theorem, but just in different order. So our B squared will be 3 squared, C squared will be 2 squared, 3 times 3 is 9, 2 times 2 is 4, 9 plus 4 is 13, right? That's A squared, which means A will be positive and negative square root of 13. So if I had to write my x-intercepts, my x-intercepts would be positive square root of 13 and 0, negative square root of 13 and 0, which are not happy numbers. So where can I approximately graph positive and negative square root of 13? We need a decimal approximation so we can actually sketch our graph. So square root of 13, I don't know, give me one decimal place. What do you got?
3.6.
3.6, okay. So just as an approximate, well, 3.6, you can think of that as halfway between 3 and 4. So basically our ellipse will go, oh boy. Kind of like this. I don't know. Give it a elliptical S shape, the best that you can. Not that circles were hard enough that we're introducing ellipses now, right? Just don't give it any corners. I think the worst shape I have seen is something that ends up looking, I don't know, something with a sharp pointy end. Don't do that. You just kind of give it that smooth edges. Okay, so that was actually coming up with the graph, but we're almost there for the equation also because they did want us to find the equation here. So since this is an ellipse with a horizontal major axis, this is what our equation will be like, okay? So A squared normally ends up being the larger denominator, so it has to be under X in this case. So what was our A squared? 13, right? So that means you will have A squared over 13 plus Y squared. And again, you can kind of go back and see here, our B squared was coming from the B term, which was 3, so 3 squared was 9. So our B squared is 9. And equations for your ellipse always equal 1. Okay. So horizontal major axis, you put the larger denominator under X basically. Okay. So let's see what's happening on number 2. It's pretty much the same thing. But if you look at where your foci are, you will notice these are now going to be on the y-axis, right? Which means this time we're going to have a vertical major axis. So the given information is foci are going to be at 0, 2, and 0, -2. So again, remember, foci is always going to be no matter what, okay? Then they are telling us x-intercepts are at 2, 0, and -2, 0. So in this case, x-intercepts are now actually going to be your b variables. Again, you can look at page 2 of your handout to verify that. Same relationship between a, b, and c. So a squared equals b squared plus c squared. B is +2. C in this case is also +2. So you're basically taking 4 plus 4, which gives you 8. So plus or minus square root of 8. Since it's a square root of 8, it's not a perfect square. Simplify it. 8 can be broken down into 4 times 2. 4 will come outside as 2, and 2 will continue to stay inside. In terms of graphing, again, we need to know what that approximate value is. And this time, the a values are actually giving us the y-intercepts. Sorry, that should be a 0, 2 square root of 2, and 0, -2 square root of 2. So whatever those decimal approximations are, go ahead and tell me what you think those come out to be. Okay, so let's see, we had x-intercepts at 2 and -2, foci at 0, 2, 0, -2, and what was the approximate for our square root of 8?
2.8.
So that will help you draw where your y-intercept should be. 2.8, so just a hair underneath 3. Course it should be. Not quite as circular as I drew it. You should see just a little bit of a longer side on the vertical major axis. Okay, now for the equation. So this is a vertical major axis. So remember, the larger denominator will now be under y. So that means a squared goes under y squared, and b squared goes under x squared. So a squared was 8. What was b squared? 4. So that's going to be your equation. So literally, the larger denominator goes under where you have the longer axis at, basically. Now, all of these examples for ellipses that we are doing are centered at 0, 0. We're not looking at anything that goes away from the center of 0, 0, okay? So this was basically given the foci and either the x or the y-intercept. How do you calculate the equation and then graph? Now this next set of examples is asking us to sketch the graph based on the equation and then of course identify what the foci of the ellipse will be. So which variable has a larger denominator? X, right? X has the 16 underneath it, the Y has the 4. So that tells me we have a horizontal major axis, okay? Because the larger denominator is under X, so that X axis ends up becoming the larger one. So the way we go about working with this guy so larger denominator under X, so that's the A square, which means A is square root of 16, which is 4. Automatically, B squared will then end up becoming 4, which means B is going to be the value of 2. So as far as graphing this guy goes, you are going out 1, 2, 3, 4 on the x-axis, and then 1 and 2 on the y-axis. So negative 4, positive 4, positive 2, negative 2 will end up basically becoming your x and y intercepts. Right? So it's kind of like how we talk about finding the radius for a circle. In this case, you need to find out where they're going to be crossing the x and y intercepts at. So your x-intercepts basically end up becoming negative 4, 0, and 4, 0. And your y-intercepts end up becoming 0, 2, and 0, negative 2, which is coming from your a and b values. However, they are still asking us to identify the foci. So that means we fall back to the relationship of a squared equals b squared plus c squared, right? Because we need to find out c for our foci. So a squared was 16, b squared was 4. So what does c squared come out to be? 12. Can we simplify square root of 12?
It would be plus or minus 2 root 3.
Yeah, because 4 times 3 gives us 12. 4 comes outside as 2. 3 continues to say, so our foci is basically, and of course since my horizontal major axis is a longer one, foci have to fall on the x-axis, so they will be 2 square root of 3, 0, and negative 2 square root of 3, 0. Okay, so start by looking at which variable has a larger denominator, because that's where you will be crossing that axis at. So since my larger denominator was under x, I'm crossing the x-axis at basically square root of 16, which is positive and negative 4. And that means my y-axis, y-intercepts are going to be a positive and negative 2. Which also means your focus or foci were going to fall on that x-axis. Now this example, of course, is talking about the other orientation, because you can see my larger denominator 36 is underneath the y, which means I'm going to have a vertical major axis. So my larger denominator is under y, that's going to be our a squared. Square root of 36 is 6, which means I am getting my y-intercepts from there. B squared will be the other denominator, which is 9, which means b is going to be square root of 9, which is 3. So y-intercepts at positive 6, negative 6. X-intercepts at positive 3, negative 3. So vertical major axis. So larger denominator under y, which gives you the y-intercepts. And that means the smaller denominator gives us the x-intercepts. Okay. As far as finding the foci goes, go back to that relationship between your A, B, and C values. So A square is 36, B square is 9. So what is C square? 27. So C will be plus or minus square root of 27. Can I simplify that? Yeah, because 27 can be broken down into 9 times 3. So that simplifies into 9, which comes outside of 3, and 3 that stays inside. Now remember, you have a vertical major axis, which means our foci are falling on the y-axis itself. So these ordered pairs will be 0, 3 square root of 3, and 0, negative 3 square root of 3. Okay. Questions on number 4? We're of course not doing the off-center ones, okay? So don't have to worry about that, which means we're actually reviewing circles at this point because we talked about circles right at chapter 1. So they're just bringing that idea back in here. Basically what's happening with an ellipse is if I take the two foci and bring them together, it actually forms one single point, which ends up becoming the center for your circle. And then of course the distance between the center and the edge of your circle becomes your radius, right? So it's basically a special type of ellipse is what you have with the circle, where the two foci just end up coming together and becoming one single point. So you can see they're calling it a special case of the ellipse. So the general form of your equation for a circle, x minus h squared, y minus k squared equals r squared. So the h and the k will give you the center of your circle. Again, keep in mind, guys, this is part of that transformation equation. So if you have a negative sign, that means the number itself is positive. And if you have a positive sign here, that means the number itself is negative. So when they're asking us to write the equation of a circle, now if it helps, and you don't have to, but if it helps, you can remember for a circle, which is centered at 0, 0, you can actually just have this form of the equation, right? X squared plus y squared equals r squared. When it's centered at something other, then you have the one with the hk. So either way, you can remember both equations, or basically just put 0 and 0 for your h and k, and you get the same equation. So for number 6, when they're saying write the equation when you have a center at 0, 0 and a radius of 2, what do you think that equation will be?
X squared plus y squared equals 4.
Yeah, so use that first one if you want. X squared plus y squared equals your radius squared, right? So x squared plus y squared will stay as it is. 2 times 2 will become 4. Okay, don't worry about 7 and 8 because I'm not giving you those examples. We did actually talk about these in chapter 1 where you had to use the distance formula, but we're not going to worry about that for chapter 7 here. So let's actually get into these graphing examples. They're saying determine the center and radius and sketch the graph. So now that our equation is given as x squared plus y squared equals 100, what's your center?
0, 0.
0, 0, yeah. So if the equation is x squared plus y squared, there's no plus or minus h or k happening. That means our center is at 0, 0. Now, if the basic equation is with r squared, then what do you think r is going to be when r squared is 100? Yeah, take the square root of that number. So whatever number you have on the right-hand side, take its square root, and you get your radius. So if you want to draw your circle, you can use just the distance of 1, 2, 3, 4, all the way to 10. If you want to make the distance smaller on your graph, you can go in counts of 2. So you can just go out till 5. It's up to you how you want to do it. If you're going all the way to the end, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because that's what I'm kind of seeing you guys do here. Yeah, I'm going to end up with an ellipse instead of a circle. Okay, it's something like that. Center at 0, 0, radius of 10. But what if you have something like number 10? What do you end up doing in that case? So let's identify our center and radius first. So since both of these are x minus 1, y minus 2, what kind of values will we have for our center? Positive what?
1, 2.
Yeah, so the x value becomes your x coordinate, y value becomes your y coordinate, right? The only thing, guys, I can tell you is keep track of your signs. So when it's minus, the number itself is positive. Let's say this guy was y plus 2, then your 2 would have become negative 2. Because I know in my math lab, it kind of keeps changing signs. Again, since it's auto-generated, some of them can be positive, some can be negative, so just be careful. What's the radius for this guy? Yeah, again, take square root of 4, which will give you 2. So start out by first marking your center. So our center will be at 1 and positive 2, right? And then start counting out 2 units from there. So that will be 1, 2, 1, 2, 1, 2, 1, and 2, right? Like I said, it's really a review of what we did in chapter 1. There's nothing new that we are introducing here. And I actually took 11 and 12 out of your homework. So you don't have to worry about 11 and 12. So that's all we're really doing with circles, is how to graph them and how to identify our center and radius. So questions, like I said, 11, 12 are out. Questions on the ellipse and circle. Okay. Again, we're doing a very toned down version of 7.3. Now remember, with hyperbolas, you can have two branches. In practical use, sometimes you may actually only see a single branch, but obviously since we're studying these algebraically, we want to talk about both branches of this. So remember, even though they sort of look like parabolas, each branch is not a parabola. For one, they don't really have that symmetry that a parabola has. And the reflecting property for a hyperbola is actually pretty interesting. Kind of like what we saw with an ellipse, that it starts at one focus and goes and gathers at the other. So each of our branches will have its own focus point. And as you can kind of see in that right side image, we're basically saying a light ray aimed at one focus will be reflected at the other one. So basically the idea is, think about again, and I think they're using the idea of a telescope here. So we've got this light coming from the outer planets, right? This is the two lights you're seeing right at the top and bottom. It's coming in, it's actually hitting a parabolic surface. So this one actually is using a combination of parabola and hyperbola. So this is actually this curve that's formed with these two mirrors right here is a parabola. What we're doing is we're using the parabola to break off that reflection so it doesn't go all the way. And we're using this focus, which is actually the focus for this parabola right here. So it's getting focused. The light that's coming from this outer planet is getting focused here, so that now I can bring in my hyperbola and help it hit the other end of the focus. So now, using this same focus, which is part of our parabola also, but now is the same focus for this hyperbola. And you can see that branch right here, because that's what this mirror is doing, is giving us this hyperbolic shape. So now this light, which is getting reflected at this point, is now being sent back towards the second focus, which is basically the second focus for the other branch of our hyperbola. And this is where we're actually putting the eyepiece at, so that you can actually see. So what happens is you're using the parabola to come and reflect and direct it towards the second focus, and that second focus will send it to the first one, so that we can actually see the planet or whatever details we're hoping to see a lot better. So it's kind of actually interesting that you use both hyperbolic and parabolic surfaces in a telescope to get a better viewing. And they're kind of getting into a little bit of that description here. So just your definition for a hyperbola is a set of points in the plane such that the difference between the distances from two fixed points is constant. So with the hyperbola, you can of course have hyperbolas that are opening left and right, which means our focus will fall on the x-axis. But you can also have hyperbolas that open up and down, which means your focus will fall on the y-axis. Now look at how these equations look compared to our equations for ellipses. So with hyperbolas, you actually use a minus sign in your equation. So the plus sign tells us we're looking at an ellipse, because basically plus tells us it's a closed circle. The minus is telling us it's going away from each other. So a hyperbola will be x squared over a squared minus y squared over b squared equals 1. So how do we know, just by looking at the equation, that is our hyperbola opening left and right, or is it opening up and down? Which variable is mentioned first is what happens. So with ellipses, which denominator has the larger number is how we know what the ellipse looks like. But with hyperbolas, it's which variable is first. So if we say x squared first, it's a hyperbola opening left and right. If we say y squared first, it's a hyperbola opening up and down. So it's actually which variable does your equation show first? X squared opens left and right, y squared opens up and down. We're still using the letter C to talk about foci. So for the the hyperbolas opening left and right, you will have C0 and negative C0. For hyperbolas opening up and down, of course, it's going to be on the y-axis, so it's 0, C, 0, negative C. The A values will represent the x-intercepts for left and right, and the A values will represent the y-intercepts for up and down. So it's the A which will keep changing positions here. But C, of course, will still be used for focus. Now, this is the relationship between your A, B, and C values. I actually don't like the way they have this written down. So what I normally do is take that A to the other side and think of it as A squared plus B squared equals C squared. If you can really remember the relationship between Pythagorean theorem, that's the exact same thing that's here. A squared plus B squared equals C squared. So before we actually get into any examples, let me write a little comparison thing down. So for ellipses, so if A squared is larger than B squared, you have a horizontal major axis, right? Because the larger denominator we're putting under x. But if we put the larger denominator under y, you have a vertical major axis. So this will basically be an ellipse that opens like this. This will be an ellipse that opens like this, okay? And the relationship between A, B, and C is going to be A squared equals B squared plus C squared, okay? That's for an ellipse. For hyperbolas, we've got x squared over A squared minus, okay, y squared over B squared equals 1. So since x squared is the first variable, this is opening left and right. It's going to open like this, okay? If, whoa, what are you doing? Don't tell me I lost the whole thing. Okay. There we go. If y squared is the first variable that's mentioned, so you will notice in this case my A and B values don't actually change. It's the numerator that's changing. So if the y squared is mentioned first, that means we have a graph that's opening up and down. Okay? And the relationship between A, B, and C will be A squared plus B squared equals C squared. So the big difference you should see is how we're defining A, B, and C for ellipses, which is A squared equals B plus C, right? It's B squared plus C squared. Whereas for hyperbolas, it's like a Pythagorean theorem, a squared plus b squared equals c squared. So getting this differentiation is going to be a very big part of recognizing, do you have an ellipse, do you have a hyperbola, and how they're open. All right, let's talk about how can we graph these guys. So for a hyperbola, to be able to graph them, we actually need to be able to draw this fundamental rectangle. So you have to actually draw these fundamental rectangles with our oblique asymptotes, because the asymptotes will tell us how to bound our arms, you know, how those arms are going to come out looking like. So basically, if it's a hyperbola opening left and right, we'll have x-intercepts. If it's a hyperbola opening up and down, we'll have y-intercepts. Figure out basically where our foci are going to be, and then of course, the values for our fundamental rectangle. And they're actually talking about draw the rectangle through positive and negative a and 0, positive and negative b. But this is what I actually like to do when I'm working with graphing for hyperbolas. Okay, so for this first example here, they are telling us to determine the foci, equations of the asymptote, and sketch the hyperbola. So you can see we have the x variable mentioned first, right? So it doesn't matter where the larger denominator is, it's which variable is mentioned first. So since x is mentioned first, that means our x-intercepts are coming from the values of positive and negative 2. So you're actually going to have positive 2 and 0 and negative 2 and 0 as our x-intercepts. Our b values are of course going to be coming from 9, because if this guy is a square, obviously 9 has to be b squared. So if b squared is 9, that means b is 3. You can kind of, in a way, think of b being your y-intercepts, but our graph is not actually crossing the y-axis at all. So this is actually going to come into handy for our fundamental rectangle, basically. So if I draw my little graph here, this is our x and y, and see we're going out to 1, 2, maybe 3, 4, 1, 2, 3, 4. Okay, we know for sure we're going to have our x-intercepts at negative 2 and positive 2. Okay, for the fundamental rectangle, the 4 vertices or the 4 corners of our rectangle are actually going to be these a and b values. So since this is a hyperbola, that because my x-axis first opens left and right, the a's are my x values, the b's are my y values. So the 4 corners for a fundamental rectangle are going to be a and b, negative a, positive b, positive a, negative b, and then negative a, negative b. So they're basically just combinations of positive and negative. So in numbers, they will be 2 and 3, negative 2, positive 3, positive 2, negative 3, and then negative 2, negative 3. So if I use these vertices, 2 and positive 3, 2 and negative 3, negative 2, negative 3, negative 2, positive 3, you get your fundamental rectangle, just using those 4 points and joining your sides, right? These are all imaginary shapes, so that's why we're not drawing them as solid lines. And I just said that after Robert drew his solid lines. So dotted lines, dashed lines, okay, because these are not part of our graph. These are just supporting lines. They also said we needed to have oblique asymptotes. Now, to graph the oblique asymptotes is actually not that bad because you just pass through the center, right, which is at origin, and then you're going through the opposite corners, right? But when it comes to the equation, because they are actually asking us to write the equations of these asymptotes, that's the one part we gotta be careful about, because since this is a parabola opening left and right, these equations are going to be in the form of b over x and negative b. Sorry, negative and positive b over a times x. So b over ax, negative b over ax. So for our example, our oblique asymptotes, excuse me, b over ax and negative b over ax. And of course, these guys are equations, so it's always going to be y equals. So for us, that will be b is 3, x is 2, right? Or a is 2, and y equals negative 3/2 x. So this is just to satisfy that condition of what the equations will look like. But for our graph, as far as the graphing goes, just start at the center, go through the diagonal endpoints. And obviously having a straight edge makes a whole lot of difference. The fundamental rectangle is the most important part of drawing a hyperbola. Everything else, we have our x-intercepts, we know they're crossing at 2 and negative 2, so it's actually going to go a curve which gets blocked by that oblique asymptote there. This curve, which will get blocked by the oblique asymptote on the bottom. Same thing on the left. And please make sure you're actually crossing the x-intercepts at those points, negative 2 and positive 2. A lot of times I'll see students leave little gaps. So you're basically touching that side of the triangle when you draw your branches. Now, we've got our graph, we've got our oblique asymptotes. The only thing we are missing is the foci. So for the foci, remember this is where our relationship comes into place. This is the Pythagorean theorem, so that's a squared plus b squared equals c squared to help us remember the relationship. A squared was of course coming from 4, b squared was coming from 9, and remember those were our original denominators for the equation. So c squared equals 13, that means c equals positive and negative square root of 13. Can I simplify that radical? No. Excuse me, another thing to remember, this is a hyperbola opening left and right, which means our foci are going to be on the x-axis. Excuse me. So when you have a hyperbola opening up and down, these relationships are going to change. Excuse me. So the first thing you should notice is how the equation of the asymptotes have changed. Instead of having B over A, these guys are now A over B. Okay, I don't have it written down. But the other thing you should notice is these fundamental ordered pairs, or the fundamental rectangle will also change. They will become BA, right? Positive and negative. So BA, negative BA, positive B, negative A, and then negative B, negative A. So basically just switch your ordered pairs. We're not doing these. And I actually can't remember if we are doing. Okay. I actually can't remember if we are doing these or not, but let's say if we are, so it would be something like this, not the other one. So it would be foci, remember, always gives you the C values. Now this point, is this going to be on the x-axis or the y-axis? X-axis, right? So that means this is a hyperbola opening left and right. So if this is a hyperbola opening left and right, that means this equation will be starting with x squared over a squared minus b squared over y squared over b squared equals 1. So you're getting your C value from here, and the x-intercept gives you A or B when it's a hyperbola left and right. It gives you the A value, right? So use the relationship of A squared plus B squared equals C squared. We've got A squared as 3 squared, which is 9. C squared as 5 squared, which is 25. Use that relationship between A, B, and C and calculate your B value, and then just put it under the denominator. So I honestly don't remember if you'll see something like 6. Give it a try and tell me if you have any questions. So here's the deal, folks. If you have not taken your